go to the fourth presentation. Improve the multi-step, multi-variate, and spatiotemporal quantitative usage forecast. Speaker is this speaker's
Hello, I am from Research Lab. So I will present the paper Improve Multi-Stage, Multi-Variate, Spatiotemporal IT Data Usage Forecasting without deploying the data. So let us consider the scenario where a lot of mobile users or network users are traveling inside the city. Huge movement data, completely dynamic environment is there. And other challenge is like the data you collected is still not 100%, some around 30% to 40% data you can see. So one solution in that case, like you can apply some data imputation techniques, either supervised or unsupervised. If you use the unsupervised, then you will add some noise, good amount of noise in your data. If you use supervised, then you at least need for some interval full data, but here it is not available since the starting point. That's why we decided to go with a technique which may not rely on those kind of missing data and still work better than the state-of-the-art techniques. So this is just general definitions of multivariate time series forecasting. So in our case, we are using multivariate, means we are forecasting multiple features, but we added some additional things like we are using multi-state also. Multi-state means we are forecasting for multiple time intervals, and then spatiotemporals means we are forecasting for each of the sets, means some spatial components are also there. So this actually creates a lot of challenge. So these are some challenges like dynamically changing traffic patterns. And another challenge is missing data availability, quality. If you actually go to the data that is available to do the research work for 5G forecasting, it creates a lot of noises are there. We try to normalize it to some max value or median value because sometimes data is too high. So we decided to select some median value and normalize the data to make it correct, little bit correct. And these are some use cases where it can be used. So here you can see that if you have a better forecasting, such kind of forecasting methods, you can do the cost reductions, better resource allocations. We can mitigate the network failures because you know the forecasted value that what are the resources which are available, network resources which are available. So you can directly route those resources to area where some network failure happens. So you can maintain such kind of things. You can improve the network resilience also. You can handle the dynamic rescheduling also. So how to solve this problem? To solve this problem, actually what happens? We have used the Milan data set, like I discussed here in this section. I have used the Milan data set. So this data set actually contains the data collected for the Milan city, and they divided the entire Milan city into 100 into 100 grids or cells. So here you can see the traffic moving patterns, like people are moving from here and there, and Milan is a tourist place in Italy. So a huge movements of people and means person who use the network resources are there. So in that case, even if you consider the cell, you will find that there are impacts on other cells, nearby cells impact will also be there when you will forecast, do any kind of forecasting. So that's why we designed our network such that we have used the cell kind of scenarios like that, and we can see that to forecast this, we have just considered the adjacent cells, like adjacent cells we consider, and we use the information from adjacent cells in forecasting for the central cell, so that we can capture the dynamic movement also. Now, how we designed the simple network to forecast the multivariate, multi-state and spatiotemporal forecasting. So here you can see that these are the adjacent cells. So I just explained the entire algorithm architecture with respect to C0 and adjacent cells. So it takes the input from all the adjacent cells and the central cells, and after that data is passing to the LSTM blocks, and it takes the last hidden layer output of the LSTM blocks. So last hidden layer output generally gives the summary of the entire data section, and after that it gives the summary of the similarly last hidden block of the central cell. So you get the summary from that also, and after that we concate the entire information here. One more thing that is important, that we are following the order. For example, we are following like this order, clockwise order in every case, because, and this creates a shallow graph also, shallow graph kind of architecture with stable round, means stable rotation, fixed kind of rotations, so that we can effectively capture the spatial location. If we just use the graph, then there is a permutational invariance related issues with graph. Means some graph node rotations will there, and then it will totally destroy the entire system, spatial features. After that, we have taken this to some perceptron layers 1 and 2, and we get some input from those two perceptron layers, and then we concate this summary output with the central cells output, which are coming through the LSTM blocks. So we combine those two kind of summaries here, and after that we use the repeat vector. So use of the repeat vector is like, because we are using, for example, in our case we are using the multi-stage time series forecasting. Means we are forecasting for multiple times. For example, they are just t plus 1 and t plus 2. So two time intervals are there. So that's why here you can see that repeat vectors just repeated this output for 2 times, and then for each of the repeated vectors after output we applied the self-attention mechanism. The main use of this self-attention mechanism is to learn the importance of each of the features with respect to each of the output for which we are providing the output time steps, so that it again we feed those self-attention output to LSTM blocks. But here, instead of taking the last hidden layer output, we are taking the output from each of the blocks, so that we can get more representation for data. And then we provided it for time distributed wrapper. So time distributed actually contains multiple layers. So if you want to forecast multiple features at the same time, then Keras or TensorFlow libraries provides a kind of wrapper which contains multiple hidden layers. So for each step, it will provide up to k features. For second, it will provide up to k features. And as here self-attention layer is there, so based on the data given, it will automatically update the feature according to that. Now the next thing that is very important, because I said in our case 35% data is missing. So you cannot take the complete time series, like take the 24-hour time series and forecast for next 24-hour time series. And when we are not using data imputation technique also. So the solution is, we can work on smaller patterns. For example, one of the smaller patterns that we got that is highly effective in this case, like a sequence length 7, means take the 5-hour input and forecast for 2 hours. So how we selected this sequence? For that we developed a simple longest frequent sequence identification technique. It is just a repetition based grid search kind of technique which identifies that what are the longest possible time sequences which exist more than 50% time in the entire data set. Then after going through that, we find that the longest possible time series, the time patterns, continuous time data. For example, there is no missing, no gap between hour 1 to hour 7. So such kind of data, how many times it is there in the entire data set. So the task was to select the largest such kind of sequence. So based on such kind of grid search based, we identified that in this case, Milan data set 7 is the best data. So after that, I already explained that this is the data set, input output patterns, data input patterns, these are the cells, adjacent cells. So here you can see that some other details, internal details, like the LSTM that we used, this LSTM, this is called, so this is a bi-LSTM, and bi-LSTM here, the bidirectional means here they are concatenating the two outputs in a layer output. And after that, we have used the PNN layers. So this is the general activation layer, then weight matrix, and then input, and then bias structures. So similar kind of architecture is there. And for concatenation layer, here you can see that we concatenate this output with the output we are generating from here. So here we have defined that repeat vector, how it repeats the output to multiple times, like how many times you require for different time stages. And another thing is like time distributed wrapper. So time distributed wrapper, we say that, for example, if you want to take some output and predict multiple feature output, so for that, the time distributed wrapper is ready-made in TensorFlows and Keras related libraries, but for other you have to write code so that it can just give the activation layers and a functions which to for each of the features output. Okay. And here this is the shape potential layer. So here you can see that this is just Vaswani's papers related things. So this is the data related thing. So this is date time. So mainly we are using some additional features like date time, weekday, holiday, weekend, weekday, kind of additional features that we inserted. And after that, missing data. So these are the results. So actually, after collecting the adjacent grids of the data, we find that our results are better than state-of-the-art results in a lot of different ways. And the system is lightweight, so it is faster. Actually, in the state-of-the-art paper, the complete architecture is not there, so we cannot say that how they have compared. But in our case, we have used A30 system to generate all those results. And we have used mean absolute error. So the results are like average mean absolute errors. So we also tested, like in our case, like if we increase the number of missing data, then what happens? Then up to 40% missing data, the system is working effectively. But if we increase the missing data, like more than 40, you can see that accuracy it started decreasing if we increase the missing data. And so here we can see that entire diagram, like this is the Milan city grid, how the cells are divided in the entire data set, and how we have developed a dashboard also. Here you can see that how the system works like that. For example, incoming text incoming, text outgoing. So it predicts like at a time like 4 hour morning, this is the scenario. So when it increases the time, okay, morning 4 o'clock, so this is the scenario of the entire. So after predictions, we map the results to see that how it works. So for example, if we change the timing to some evening time, like okay, so 5 o'clock evening. So see the scenario, it totally changed. So how entire usage changed. So you can see that it shows the entire results based on the grid, like where it is there, and you can see this grid like what is there. So why I said that we can use this for resource utilization. For example, here you can see the data. This is data usage. This is data usage. But there are some resources are available, bandwidth are available. You can use it to means allocate the resources and so this is the one.
Any questions?
I have a question. There is some kind of age of information. So that means your training data could be some amount limited.
Yeah, 80% training data I will use and 20% for this, like the state of the art use. So it is like in Milan dataset, you will get dataset from November to December and then till January 1st. So mostly what other papers also did, they trained the system from entire November data and till January 20th data. And for rest of the data, December 20th data, and from December 21st to January 1st, they use for this. The same way we have used.
I see. Thank you. Thank you so much.
Thanks.
So we move on to the last speaker.